Trigonometry, Chapter 5, Trigonometric Identities, Section 3, Sum and Difference Identities, Video 1, Deriving the Cosine Difference Formula. This series is based on content from Pearson's Trigonometry 12th edition by Lial, Hornsby, Schneider, and Daniels. In the previous section, we verified trig identities. We explored key algebraic maneuvers that, when combined with fundamental identities, allowed us to prove new identities. In this section, we develop and implement new identities for the sum and difference of two angles. In this video, we develop the formula for cosine of A minus B. Now, intuitively, one might think that cosine of A minus B is equal to cosine A minus cosine of B. While this seems okay, it's easy to prove this is not the case. If they are always equal, then they must be equal for specific values of A and B. This is a classic way of disproving something as an identity. Show it fails once. So what would each expression equal if A equals B equals pi over 4? And when I say each expression, I mean cosine of A minus B versus cosine of A minus cosine of B. Well, if we did cosine of A minus B, then that would be cosine of 0, which is 1. But if we did cosine of A minus cosine of B, we would get 0 because A and B are the same. And so the difference in their cosines would be 0. Clearly, these are not the same values. As such, cosine of pi over 4 minus pi over 4 is not equal to cosine of pi over 4 minus cosine of pi over 4. This means we cannot say that cosine of A minus B equals cosine of A minus cosine of B as a general rule. So what can we say about cosine of A minus B? Before we go any further, I need to put out something from a logical perspective. If these expressions had ended up being equal, we could still not draw this conclusion, because showing that it's equal once doesn't mean that it's equal all the time. So be careful. One instance of evidence of an identity being true doesn't mean it's always true. In fact, no finite number of instances of evidence can verify that an identity is true. However, one instance of it being false is good enough to say it's not always true. Now, to derive an identity for cosine of A minus B, we're going to consider the following illustration. We got this triangle situated in a unit circle. We can tell it's a unit circle because the point on the right is 1, 0. We're going to look at certain angles in here, starting with angle POQ, the one in standard position highlighted in green. We're going to call the measure of this green angle B, and because this is a unit circle, that means the coordinates of point Q are cosine of B, comma, sine of B. Now let's look at this angle also in standard position, POR. We're going to call the measure of this red angle A, and because this is a unit circle, the coordinates of point R would be cosine of A, comma, sine of A. Now we're going to apply the distance formula to segment RQ, since we have representations for its coordinates. If we did the distance from R to Q, it would be the square root of the sum of the squares of the differences of the coordinates. Here's the difference of the x coordinates squared, and here's the difference of the y coordinates squared. We'll come back to this expression momentarily. But now we're going to consider this purple angle between QO and OR, so QOR, not in standard position. However, notice that the green angle plus the purple angle would give us the red angle. And if you want to see a more visual, the green angle plus the purple angle equals the red angle. And because of that, if we solve for the purple angle, we would get that the purple angle is the red angle minus the green angle. But the measure of the red angle was A and the measure with the green angle was B. So the measure of this purple angle is A minus B. Cool. Now we're going to rotate this purple segment, this triangle, by an angle of B. Remember, B was the green angle here. So if we rotate it B degrees or B radians clockwise, then this triangle is going to land on the positive x-axis, and we're going to rename it Q prime O R prime to keep track of where Q and R go. So here's the triangle rotated with Q prime and R prime. Same triangle, it's congruent. Now notice that Q prime does land at the point P, so it's 1, 0. And since the purple angle is now in standard position, the coordinates of r prime are cosine of that angle, a minus b, sine of that angle, a minus b. Now we're going to apply the distance formula again to q prime r prime because we have representations for the coordinates of q prime and r prime. And when we apply the distance formula, it's the same idea. It's the square root of the sum of the squares of the differences of the coordinates. Here's the difference in the x coordinates, that difference squared. Here's the difference in the y coordinates, that difference squared. Now, because we rotated the triangle and the two triangle, excuse me, because we only rotated the two triangles are congruent, which means RQ is congruent to R prime Q prime, which means the distance from R to Q is the same as the distance from R to Q prime. Therefore, we can equate their distances. This is the expression that we got for the first distance. This is the expression that we got for the second. And now we're going to do some algebraic manipulations with a smidgen of trigonometry. We're going to square both sides, which gets rid of the square roots. Now it seems we have 4 squared binomials, but only 3 of them are truly binomials because this fourth one is -0, so it's not really a binomial. It's just the square of this sign. All right, we're going to square all 3 of the binomials quickly. You can think of it as writing each binomial twice and foiling it, or if you know the formula for squaring the difference in 2 terms, you would get this hot mess. The first, second, and third ones all squared. Now, if you're trying to write all this down, obviously you should pause the video. But if you know how to square a binomial, then there's no need to write it all down. Just watch what happens. Now that we've got this mess of terms, we start looking for things that we can do something with. And I notice a lot of squared trig functions, which makes me think Pythagorean identities. We have 3 pairs that we can capitalize on. The yellow ones, the orange ones, and the dusty pink ones, whatever color you would call that. Each of those pairs is the sum of the squares of sine and cosine of the same angle. Cosine squared A plus sine squared A, cosine squared B plus sine squared B, cosine squared A minus B plus sine squared A minus B. Well, according to a Pythagorean identity, all of those equal to 1. 1 second. All right. Had to pause for a moment to take care of something. So don't quite remember the last words that were coming out of my mouth. So we'll just pick it up from here. Excuse me. So anyway, we have these pairs of squared trig functions whose sum is 1 because of the Pythagorean identity, sine squared plus cosine squared equals 1. So everything you see is about to transform into the number 1. The number 1. There we go. So we had a pair of 1s on the left and a 1 on the right. Now notice we also have a 1 on another one over here. Where did this one come from? That one came from right here. It was the result from squaring this binomial. That 1 squared became this 1, so we've got this stray 1 floating around. So we got a pair of 1s on both sides, which we can combine to make a 2, and then subtract 2 from both sides to make them both vanish. So all the 1s eventually disappeared. Now, if you notice all 3 of the remaining terms, the product of cosines, the product of sines, and the cosine of A minus B, have a coefficient of -2. So we can divide everything by -2 and get this, which is exactly what we wanted, an identity for cosine of A minus B. We'll rewrite it with the cosine of A minus B on the front. Eventually, there it is. We now have this identity. Now, there is no now you try for this video because we're developing the formulas. So instead, I want you to focus on the structure of the cosine difference formula, which is technically an identity. Cosine of A minus B equals cosine of A cosine of B plus sine of A sine of B. The cosine of a difference is the sum of the product of the cosines and the product of the sines. I want to leave you with a device for remembering this. I know that in some classes you may have this formula provided for you on test or in your notes, but if you were to try to memorize this, and for those of you going into calculus and beyond, trust me, the more you have memorized, the better. When I was tutoring pre-calculus in the early 90s in college, I remember tutoring this lady over what we're doing right now, and she was good at coming up with gimmicks for remembering things like cosine of A minus B equals cosine A cosine B plus sine of A sine of B. And I wish I could remember her name so I could give her credit for this. But I remember her thought process went something like this. Well, the word cosine sounds like the word cousin, which means the cousins are over here. They stay together. These two stay together, they're cousins. These two stay together, they're cousins. I was like, well, that's good, but how are you going to remember that the minus becomes a plus? And she thought about it for a second and said, well, that's kind of crazy, which starts with C. So cosines are crazy cousins. Cousins in the fact that they stick together and signs stick together, and crazy in the sense that the sign changes. So her gimmick for remembering this was cosines are crazy cousins. I can't remember her name, but I remember the gimmick to this day, some 34, 5 years later. But anyway, there's the cosine difference formula.